technology is called Composite Fiber Co-extrusion technology, or CFC technology. And this is important to correctly decompose this name, Composite Fiber Co-extrusion technology. It's actually composite fiber co-extrusion, so the co-extrusion of the composite fiber, but not the fiber co-extrusion, which makes composite materials. So it's actually, there's two main parts in the name of the technology. First is composite fiber, and second is co-extrusion. So what is actually the composite fiber? What is it, and why it's called that way? So as you may know, the composite materials consists of minimum two components, one of which is the reinforcement and the second is a matrix material. Reinforcement makes all the properties, brings all the properties of the material, and matrix makes the similar reinforcement elements work together. And in fiber reinforced composites, it's actually the structural fibers such as carbon, glass, or aramid are normally used as a reinforcing, and different types of matrices. In most of the cases, it's polymer matrices are used as a matrix material. So why it is called a composite fiber? So it is not the raw material, it is not the dry fiber. So as a part of the technology, as the first step of the technology that we do internally, and this is our patented process, we pre-impregnate dry fiber roving with a special resin, and to make sort of a pre-preg material, a preliminary impregnated material, and then we fully cure this material, and then we have the stiff, fully impregnated, very stiff fiber material, which we call composite fiber. And we have two types of composite fibers available. One is based on carbon, and second one is based on basalt fiber. This is what is important to understand about that it is already a composite material. That's why it is called composite fiber. These fibers, these preliminary impregnated fibers, we use as a feedstock, as a feedstock material in the printing process, in the co-extrusion process. So on all our machines, to print with continuous fiber, you need this fiber pre-preg, this composite fiber, which we produce and which we ship on spools. You need this material to be able to benefit from the continuous fiber printing. The material itself has characteristics that you can see on the page on the left. So this stiff filament with, if we're talking about the carbon, for the CCF, it's a very thin and very stiff fiber, which has an effective diameter, which has a round cross section, and it has an effective diameter about 350 micron, and it has about 60% of fiber, of pure fiber by volume, and about 40% by volume of special matrix, of a special resin. The mechanical properties of this fiber, of the fiber itself, are very high. So the elastic modulus of this material is more than 150 GPa, and the tensile strength is over 2 GPa. So it's many times stronger than steel and all other metals. In the co-extrusion process, we process this fiber together, we extrude this fiber together with plastic material. And the final material that is printed with a co-extrusion technology, we call it a B-matrix material. It has composite fiber inside and a thermoplastic polymer as a main matrix material, and the properties of this material are shown on the right side of the page. For using CCF carbon and CBF basalt fibers together with a PETG polymer. Why do we need to pre-impregnate the fiber before printing? Why do we need to make this composite fiber, and why this is a very important step? Because the properties, the final properties of the composite material depend very much on the quality of the material, and quality depends on the level of impregnation. So to have the good quality material, you really need to have a very good impregnation with a very low presence of porosity and a very good adhesion, very good bonding between the components in the composite material. So basically between the fiber and the resin and the matrix. And low porosity and good bonding is a key to good properties, to good quality of material. This is the cross-section area, the microscopy of the cross-section area of Anisoprint CCF fiber. It's provided by our partners from Girona, from University of Girona. Here on the right, you can see this picture, this microscopic picture. You can see white dots. Actually, white dots on the picture are the microfilaments of carbon fiber. Each filament has an approximate diameter of 7 micron. So these white dots are very well distributed inside the circular shape, the circular cross-section shape of the fiber. Gray inside, between the fibers, you can see gray matter. It's resin, which bonds together these fibers. So you can see that there are no black spots, no irregularity in the fiber distribution. So it's considered to be a very good quality impregnation with a fiber volume fraction about 60%. What similar material, similar fiber can look like if the impregnation is not so good? This is an example of how it can look like with an improper or improper impregnation. So you can see a lot of black spots inside the cross-section area. You can also see the white dots, the fibers. You can see the black areas, which are highlighted. It is basically the air pores. So that means that there is no material, that there is no matrix material which bonds together the fibers inside. And you can see that the fibers are not very well distributed. You can see polymer-rich zones where there are no fibers, and you can see that the fiber volume fraction is not too high. So it's about 30, it's less than 30%. It's close to 10% of porosity. And it is actually, it's actually the a very important stage to get the good quality. So why do we need to pre-impregnate the fiber? Because if we would do the co-extrusion with just the dry fiber, with the non-impregnated fiber, such picture, as you can see on the right, would be a very good result if we can get that level of impregnation in situ with the dry fiber co-extrusion. And in most of the cases, the picture would be much worse than this one, and there will be much more pores and much more defects inside. So to get the good quality, we need a preliminary impregnation, and this is an important part of the technology. Now, what is the second part? Yeah? The second part of the technology name is a co-extrusion. Yeah? We've looked inside the composite fiber. I've explained why we need this. And the second important part of the technology is the co-extrusion. This picture explains the process schematically. So it is the composite, it is the extruder, extruder schematics, which shows that there are actually two inputs. One input is for fiber material. So fiber goes straight from the spool into the hot end, into the melting chamber. And there is a separate channel, second input for plastic material that goes on a separate channel, goes inside the melting chamber, and it mixes with the fiber in situ during the printing process. And there is just one output, one nozzle, where the mixture of the fiber and plastic, so basically the plastic which is reinforced with the fiber in this process, is deposited on the print area, on the print volume, and the B matrix material is formed. I will stop once again about this term, why it is called a B matrix material. It's a composite material, of course, which has the reinforcing fiber material inside, and two matrices. One matrix is the resin that is inside the fiber tow, that is inside the composite fiber, the resin which bonds microfilaments inside the fiber. And the second material is a plastic material, which we call a main matrix material, which bonds these composite fibers together. So in the final composite, there are actually three components: fiber, resin, and plastic, and two interfaces. There is one interface between the fiber and the resin, and interface between the resin and the plastic. There is no interface between fiber and plastic. And the approximate volume fractions of each materials are like it is 50-50 by volume of composite fiber and plastic, roughly. But the beauty of the co-extrusion technology is in the capability to vary this volume fraction, but 50% of composite fiber and 50% of plastic is an average that will give the best processability in most of the cases. And so it's 50% of plastic and 50% of composite fiber, which has about 60% of dry fiber and 40% of polymer. So in the B matrix material, it's roughly about 50% of polymer, 30% of dry fiber, and 20% of resin. I see that there are questions coming. I will answer all the questions at the end of the presentation. There will be time for Q&A session. So let me continue just as it is. On the machine itself, on the composer, which is the desktop printer that utilizes the composite fiber co-extrusion technology. The print head has actually two extruders. One is a CFC extruder, which is on the right part of it, and the second on the left is a plastic extruder, a classic FFF FDM extruder, which has just one input for plastic filament and just one output from the nozzle with a molten plastic. And the CFC extruder on the right has two inputs for fiber and for plastic and one output for composite material. It also has a cutting mechanism to cut the fiber when needed. It has the heat breaks as normally, and all other features, all other parts of the extrusion-based print head. So, what are the advantages of the co-extrusion? Why it is important for us to have this approach? First, I will start with the notion that there is no extra consolidation in the printing process, so there is no roller or pressure applied. So, as I mentioned before, in this B matrix material, we can reach on average the fiber volume fraction of about 30%, which might sound a bit low for if compared to traditional autoclave, traditional pre-preg based composites made with the traditional technologies, where you can get normally higher than 40 or up to 60% of fiber volume fraction. But to achieve these high volume fractions of fiber, there is a pressure, a high pressure needs to be applied. So it is done either by a special roller or by the post-consolidation in autoclave or press, and to get this high fiber volume fraction. But actually this brings a lot of shape limitations. Basically, by applying pressure, you cannot make 3D structures with complex shapes and thin walls. You will only be able to make flat sheet-like materials. And this is important part of the co-extrusion. So with the co-extrusion, we are not getting to very high fiber volume fraction, but by being able to vary it and by not having a necessity to apply pressure, we are able to print very complex shapes and with no post consolidation required, and good material properties and low porosity with no extra pressure applied. So this gives us a lot of flexibility, and flexibility is the most important word here, and that's what we are trying to bring with our technology of composite fiber co-extrusion technology. We're trying to build the most flexible technology for manufacturing with composite materials. So to offer our users, users of the technology to be able to print like really complex shapes and different curvilinear technology and full freedom of orientation, of choosing the material orientation and of adjusting and controlling anisotropy, both in terms of the direction of material properties and the ratio of anisotropy in every material point. So that's one of the first benefits that the co-extrusion approach gives us. Second is that also about the flexibility, but that's about the flexibility in material choice. in the co-extrusion process, the main matrix, the plastic material, is chosen at the end user side. So the user of the system can choose any plastic material in the form of a 1.75 millimeter filament, and in the co-extrusion process, by extruding this plastic together with our composite fibers, different types of materials, different types of plastics can be reinforced with carbon or basalt continuous fiber material, and making them tens of times stronger. Why it is important to have the choice, to have the option to choose the plastic material? Yes, the strength and stiffness are the properties that are defined, that are governed mostly by the fiber material, but there are dozens of other properties that might be important for different applications, such as chemical resistance, or environmental resistance, or fire resistance, or friction, surface toughness, and many other properties that are mostly the surface properties of the material, which are governed by the matrix material. So for every particular case, you might need different materials, different plastics materials, and here with this approach, with the co-extrusion approach, the end user has the capability to choose whatever plastic material he needs to reinforce. That was the second one, and the third one, and I think it is one of the most important for us, is the capability of printing lattices. I will talk a little bit more during this webinar later about lattices, but it's important to note here at this point that lattices cannot be printed with any other composite fiber printing approach because of the junctions. So lattices consists of ribs, of unidirectional ribs that have intersections, that have junctions where fibers have to intersect, and they cannot interrupt, they cannot be cut, stopped, and restarted at the intersection point. So basically what happens in the junction point, the fiber volume is doubling, and but we need to avoid, in this case, doubling the material volume. So in the intersection, actually, we need to be able to locally, in the intersection point, we need to be able to reduce the matrix volume fraction several times, to not have the increase of thickness in the intersection point, and to be able to have the continuous fibers in the intersection. That's the example. What could happen? What could happen if the plastic and fiber volume fractions are fixed? If it's just if it's just the pre-preg placement, where you do not have a separate channel, a separate stream of plastic that is controlled independently from the fiber, you will have such bumps in the intersection, increasing in increase of thickness, which first of all decreases the properties of the material a lot due to irregularity and fiber waviness, and makes it very hard to do complex lattice designs because of these variations and these imperfections in the intersections. So why? We now see that co-extrusion allows us to print lattices, and why it is important, why the lattice approach is so important for us. The explanation is quite simple, and the reason is in the anisotropic nature of composite materials. So all these high properties, in the composite materials, they are along the fiber, and across the fiber direction, the properties of composite materials are several orders of magnitude lower than in the fiber direction. But if we have a lattice structure that consists of a unidirectional ribs or of 1D ribs, so the stresses in every rib, in every one-dimensional structure, are also one-dimensional. So the rib cannot work, will not work in the transverse direction. It will only work in a longitudinal direction. It will only work along the rib. So it means that lattices, it means that composite materials with the anisotropic nature of composite materials have a very good fit for the lattice structures. So in lattice structures, composites only work along the fiber. That's why these type of structures are the best for composites. And there are actually many examples of lattice designs around us in nature. So if you look into, for example, the fly wings, these are like tiny structures, thin structures that have to be very stiff, and they have these lattices of natural fibers inside that are building these structures, and you can see how complex these lattices are, but these are still fibrous lattice structures. There were several examples of lattices in engineering, and one of the good examples, one of the famous examples, is the Vickers-Wellington aircraft, which had the lattice fuselage and the lattice wings, but it was still metal, and it was very hard to produce, very hard to make. So that's why these type of designs are not actually, didn't found their way into the aircraft design. But with composites, the lattice designs can be made even more efficient, and there are different advantages in lattice designs. Just accept their good fit to composite materials. First is that you can have a skin. You can have a skin that is not load bearing. So if the skin is damaged, if the skin is, then the cracks will not propagate, and the structure will not lose its capacity, its load bearing capacity. And even if one of the ribs in the lattice structure is damaged, then the structure will be the forces will be redistributed in the structure, and the broken rib will be just excluded from the loading scheme, and there will be no failure, propagation, no serious consequences. So these are so the high damage tolerance is one of the important benefits of lattices. Another one is actually the weight savings, and here we can go back to a 3D printing approach, and this is an example how you can save weight and optimize parts performance by using lattices. So if you are using just the plastic material, so obviously the full strength you will get with a solid, with a 100% solid part. If you introduce some plastic lattice inside, which is called lattice infill in a 3D printing, and that's the common approach to save material, to save printing time, and to save weight, your part will be always weaker than the solid one. But with composite lattice infills, where you can have a different densities and where you can adjust the directions of the lattice, you can, with just 30% of the fiber lattice infill, you will get 3.5 times increase in strength, up to 3.5 times increase in strength compared to full solid plastic. Yeah, and with just 35% of the weight. And also the print time and the material costs can be reduced. So that's why, so this is one of the examples how you can benefit from using lattices. And of course you can go more than 30, you can go up to 40, 50, and 80, and maximum a full solid composite material, which will of course have the highest strength, but also the highest weight. We have different types of lattice infills available, built-in algorithms that will build these infills in our software, in Aura, where you can choose one of 4 types of infills. It can be a solid infill, 100% solid, where you can define a layer stacking sequence with different angles, or you can choose one of 3 types of lattice infills. It can be a rhombic infill on the right top on the picture, it can be isogrid on the left bottom, or it can be an isogrid. For each lattice infill, you can define the density that can go from 5–10% up to 80–90%. And for isogrid infill, you define just one direction for the main rib, and for rhombic and an isogrid infill, you define 2 directions, so that you can have so that you can focus more properties in a certain direction. That's about lattices, and of course the co-extrusion system allows us, the co-extrusion approach allows us to make an open system. That was the point that I mentioned also before, that any type of plastic can be used as a main matrix material and reinforced, so there's a freedom in material choice. The openness of the system in terms of fiber path generation gives freedom in optimization, in design of the fiber trajectories, and the relatively low fiber volume fraction allows us to make very complex shapes with thin walls and tiny features. So not just the flat layers, yeah, but really complex shape 3D parts. So the maximum flexibility and maximum possibilities. In the last part of the presentation, I will just show a few examples, or a few use cases of the application of the co-extrusion technology. Starting from the aerospace, one of the aerospace applications. So actually this is the interior bracket it's called the monument bracket. It's the part that holds the luggage racks in the passenger jets. And originally it's made with aluminum by milling of aluminum, and it's quite load-bearing part. It has to carry at one of the load cases more than 1 ton of a load in the direction that is shown, that you can see here in the fixture, in the testing fixture. So the direction is along the bars of the testing fixture, and with the composite, with a co-extrusion approach, where we are able to make this part more than 50% lighter compared to aluminum. The second use case, the second picture that you have already seen, is about the fiber steering, and this shows what type of structures you can do by having the possibility to control the fiber directions. So obviously, if you have a stress concentrator as a whole, yeah, it's the weakest part, the weakest cross section, and for metal, for isotopic material, this is the zone where the part will break. But with a fiber steering, you can make an even stress distributed design where the part will not necessarily break in the weak zone. So basically, there will be no weak zone. So with this approach, you can tune, you can bring the material properties into the zones where it is needed. This is an example of using lattices in a tooling for tooling applications. This is actually the cold metal stamping die. So the mold that has to carry a very high pressure load, more than 400 bar pressure, and if it's made just from plastic material with a 100% infill, it will not be able to carry that load. So that's yes, that's the compression load in a transverse fiber direction. But with already 30% of the fiber infill, you can get the part that is much more durable and that can carry these high pressure loads. Another example from the aircraft interiors is the aircraft seat support. It's also originally metal part, so complex shape 3D part made with by milling, and it can be successfully replaced with much lighter, so almost 40% weight reduction compared to metal one at the similar cost. And there are a few more examples what you can do with fibrous materials, like a self-sensing, self-sensing structures, where this is actually the use case that was made by one of our customers, one of our partners, Brightlands Material Center. So by incorporating the conductive carbon fiber inside the plastic structure, and by attaching it to the current source, you can measure the resistivity, and you can measure the deformations in the structure like a sensor. There is one more example, and I think that's the last example before we go to the Q&A session. That's where you might need different matrix materials. So that was the use case made by us to the yogurt production plant. So that's the fixture for sterilization of yogurt bottles. So it has to work in the hydrogen peroxide atmosphere, and not all of the plastic materials will survive in such a chemistry. For example, polyamides will start dissolving in hydrogen peroxide, and PETG is very high resistance to this chemistry, and by using the PETG as a matrix together with a reinforcement to make the part strong and durable, the requirements are satisfied, and the part can work successfully for many hours at the production line. So we go now to the Q&A session. We have received several questions from you before. So we have asked when we were inviting everyone to this webinar, we have asked for the questions. And I will quickly go through the questions that were sent. It's actually 13 questions, and I hope that I will be able to finish them before 6:30. First question: is it possible to print your own material? If it's possible to print with different types of plastics. If it's a 1.75 millimeter filament, then you can use it, but you need our reinforcing fiber. But actually, in many cases, if you want to have the complete freedom, you can also use different types of fibers. But in this case, we will not be able to give a warranty on the print head. But actually, it is possible, and there are many settings in the software which will help you to do that if you need. Part volume limits on the desktop machines. We have two sizes: the A4, which is 297 millimeter by 210 millimeter, and the height is half of the bigger size, so 148 millimeter. Yeah, the biggest part that can fit there, if you put it on a diagonal, it's up to 350 millimeter, 400 millimeter long. Yeah. The bigger desktop machine is A3, so the build volume is 420 by 297 by 210 millimeters. So that's the biggest part that will fit into this volume. So up to half a meter, the part can be as big as half a meter. Do you foresee larger bed and or Z direction dimension machines? Yeah, the larger machine, the PRE-IMPREGNATION 500 is again twice the size of the A3. So the build volume of it is 600 by 420 by 300 millimeters. So it's again much bigger. And there are even bigger machines in our product pipeline. And we also working on the robotic system that will be available in a couple years, that will be able to put fibers in Z direction as well, not only in plain reinforcement. And we also ship such systems, such robotic systems on a project basis. So if anyone needs a robotic system or anyone has a robot, we can install our print head with the controller and do the integration into the robotic system, so that the system, the print head, will work together with the motion of the robot. what's the maximum curvature for the reinforced layer? The fiber can be bent, and it actually bent every time it's printed. It's bent in the nozzle in the 90 degrees angle. It's bent at the radius of less than 1 millimeter. So actually, when we're printing in fills, the fiber has to turn sometimes at the sharp angles, and then there is a small circle, the small curvature, of course, so it's not completely an angle, about 1 millimeter radius. But if you need to reinforce as something like a hole, yeah, the minimum diameter of a reinforced entity, like a hole, will be about 8 millimeter. Because yeah, on the smaller radius, the tolerance, the absolute tolerance will be quite low, and it will be hard. It's very hard to reinforce smaller features with good tolerance. Is it possible to print without the plastic? Only fiber and plastic for fiber. In Aura, if you are doing slicing in Aura, it's not possible to print without plastic. So Aura will always have a plastic shell, at least one external plastic shell. But yeah, we have a separate tool where you can completely freely design every trajectory for the fiber, for the plastic, with and you can print even without plastic. But this is the manual tool where you have to sketch every print stroke in a 2D CAD, like an AutoCAD in a DWG file, and then stack and then define the for every layer, and then define the layer stacking sequence, define the parameters. But this tool gives you the full freedom of designing with our machines. How at the moment is possible to validate a printed part and to satisfy the requirements needed? This is a very good question. We know how to do that, and we can do that, and we can give you some hints, and in one of the webinars we will explain how you can do these simulations yourself. But we're also working on a separate software product that will be available roughly mid next year. It is called Aura FAM, and the tool will be able to generate the finite element mesh over a sliced part in Aura. So define the finite element. The finite elements for every element. It will define the material direction and homogeneous material properties, and then it can be exported into the mesh format, into the BDF format, to be later imported into one of the common finite element simulation software, such as ANSYS, Abacus, Nastran, or whatever. So this tool will help to do these simulations more like in a more automated way, but it is possible already today. Yeah, it will require more knowledge, more skills in building the finite element mesh and in the identifying manually the material properties and the material directions. But it is also possible. How can I customize the infill like in the part? You take as example with a hole in the middle to maximize the strength. So this part, which I've showed as one of the use cases, the fiber-styrene panel, the fiber-styrene plate, was not done in Aura. So Aura it's a slicer, so it can only derive the tool path from the geometry. So basically from perimeters of the layers. So that was not the case for this example. It was made in the separate software that I mentioned on one of the questions before. So if you need to try something like that, then you need to have this another tool. But we will also have this fiber trajectory fiber path sketching capability available in Aura in one of the later versions, maybe in 1 year from now. A few questions in one. Can you print an envelope over an existing structure? I'm not sure if my answer will be if I correctly understand the question. So that means if the question is if you can put already printed or some other part into the build volume and print something over it, that's how I understand the question. Theoretically, this is possible because the system because you have an access to the G code, and you can write any G code, and you can run any G code, you can write yourself on the machine. So if you have some tool that will help you to write such a complex G code, where you might want to first print something like a fixture on the print bed, then you install the existing structure into this fixture so it's positioned in the right way, and then the rest of the G code will precisely print over it. So we do not have today tools in our software that can do something like that, but the open G code actually makes it theoretically possible for everyone who wants to experiment with that. Honeycombs of arbitrary user-defined geometry. Yes, as I mentioned, we have in Aura there are 3 types of infills, and we will add the other ones in future, but not in a short term. But yeah, you can use your own arbitrary user-defined geometry in a nano G code tool, which I have mentioned a few times before, without full curing and then form and cure finally. Actually, you can bend and form because the main matrix is a thermoplastic, so it's actually formable. So if you print the part, then if you heat it to the softening temperature, then you can form it, and then by cooling down it will keep the shape, so it is possible, but the part as you get it from the printer, so the thermoset matrix inside the part is fully cured, and the thermoplastic is yeah, it's not actually cured, it's consolidated, yeah, but you can as I mentioned, you can heat it and shape it afterwards. What are the limitations of the fiber path? Minimum stretch length, minimum arc radius. Yeah, I've already answered a little bit about the arc radius. So the turn-in radius can be is about 1 millimeter, and the minimum reinforcing radius is about 8 millimeter. the minimum stretch length depends actually on the cutting capabilities. So the distance between the cutter and the nozzle tip is 45 millimeters. So this is the minimum fiber length that you can print. What are the limitations of the fiber path? So basically, except of the minimum length and the minimum radius, there are no limitations. You can define whatever fiber path you need, but only taking into account the minimum length and the minimum radius. What are the differences between this technology and the fused deposition modeling of unreinforced plastics in terms of design, possibilities, and complexity? Of course, the continuous fiber reinforcement implies limitations. It has certain certain tolerances, because the fiber nozzle has the diameter which is quite large. It's 0.8 millimeter, and the fiber itself has the finite thickness. So, and as I mentioned, there are limitations on the radius, and sometimes the fiber, when printing, especially on high curvatures, can go a little bit wavy or drag a little bit from the trajectory. So these are some things that you need to take into account when you are designing the fiber to get the best results and to get the best quality. And of course, these questions will be covered separately in our future webinars. So there are some limitations, and it's important to understand them, and we can go into more detail about that in future. Can the instrument be adapted to print with both thermoplastic and thermosetting matrices? I'm not sure if this question is 100% correct in our case. So it is actually printing with both, the co-extrusion nozzle is actually printing with both thermoplastic and thermosetting. Just the thermosetting matrix is inside the fiber, and the thermoplastic matrix is extruded together with the fiber. You cannot use thermoset as a main matrix, as a co-extrusion matrix, because the curing cycles for thermosets are normally quite long, unless if it's not a UV curable, but the print head design and the machine is made for printing with co-extrusion with the thermoplastics. How thin walls can be? Yeah, I've already answered the question about the thin walls. Well, I've mentioned that it's one of the most popular questions, but it might need, again, I might explain it too complicated, and it might require certain sketches. So this will be also covered in the future webinars. Design pyrometer to print. So these are all the questions that we go deeper in more detail in how to design, how to properly design, and what are the settings and what are the limitations. We will quite soon release the short introductory course to the CFC printing that will be available on our webpage. And of course, we will explain these in the webinars in future. Is it possible to force Aura to cut the fiber instead of trying to make a sharp turn? Not at the moment. The Aura algorithms define the cutting points automatically, and you cannot change that. But yeah, if you want to have this capability, this complete freedom, then we have a analogy code for that. That's all about questions. And I will check if there is something else in the chat popping up. Question from Chitran. I don't think I get it, but doesn't it affect the direction of placement or direction or placement of fiber within the TP matrix? Thank you for questions, and I think that we have direct contacts, and I think the question is interesting. I don't think I fully get it, and I can try to answer it separately. And thanks everyone. If that's it, of course we can take questions separately. You can always write us when the way you prefer, either to our support portal or at support@anisoprint.com, or to me directly, Antonov@anisoprint.com, or with other means of communications, and we are always ready to answer your questions. So thank you very much for attending this webinar today. I think we are very good in timing, so we plan to have it in 1.5 hours, 1.5 hours, and that's where we are. And now if anyone has more questions, we have a few more minutes. If anyone wants to say something, to add something, I can now allow turning on the microphone, on raising hands. But for the rest, we are done. And thank you for your attention. I hope it was useful. And I hope that we will meet again in one of the future webinars. Please keep attention to our announcements, and have a good rest of the day, everyone. Thank you for attending once again. Is it? Do I see any hands raised? No. Okay. I will wait a few more minutes, and we finish. A very good question popped up. Is there any link with Professor Vasilyev activities? Of course, he is our scientific advisor, and most of the things that we do are inspired by Valery Vasilyev's works. And he was one of the persons who were standing in the beginning of the development, and we work closely today with Prism, one of our partners. And two of our co-founders, Alexey Khaziev and Andrei Azarov, are Valery Vasilyev's students, PhD students. So yes, there is a very strong link. Okay, I will end the webinar. There are no questions. Thanks, everyone. And thank you for your kind words. Thanks for attending, and hope to see you in future. Goodbye.